So welcome back to part two of compound beams, frames, machines, whatever it is that we have that we can take apart at that screw. So I just am going to go ahead and start with this free body diagram. Yes, it's a little bit neater. I went ahead and rewrote it. But remember, it's looked like this. We had an internal, we have a roller here, we had uniform all the way across, and we had a point load. Okay. So I had 1, 2, 3, 4 unknowns, which is greater than 3. So I need to have one pin internal so that I have 4 equals 4. Okay, so you guys might just want to get in the habit um, of kind of counting them up because we won't necessarily tell you that it's a simple beam or a compound beam. And if you were to try to solve this as a simple beam and not take into account there was this resistive moment at A, the whole problem is completely wrong. Okay, because this is here, I cannot sum the moments anywhere on this whole beam because not only will I have the unknown Y component if I sum about this reaction, but I also have that unknown moment. If I sum about the wall here to try to find this unknown vertical of the roller, I have to include that unknown at the wall. This is a huge mistake you guys make in statics. It's just easy to forget that this moment, resisting moment at the wall, has to be included in every moment equation. So the only way to solve this problem at this point for you all is if we give you an internal pin, which again, if I have this internal pin, I can unscrew it and take it apart on my workbench and have a left and a right side, okay? The other thing I want you all to keep in mind is many times when you all see uniform loads, you like to just go ahead and find the area. So here it would be base times height. And you like to just go ahead and put that resultant right through the centroid. If I do that with this system, knowing that this is 10 meters and this is 8 meters, I'm going to end up with a resultant over here to the left of the pin. So when I look now at the right side, I won't include any of that uniform load, and we can't do that, okay? If I were to look at the left side, I would have this ginormous vertical load that is really not representative of what's going on. So when you draw your overall, you can break it up and make that uniform a resultant force. When you take it apart at a pin, you have to go back and literally, I'm going to tell you right now, get yourself a handy dandy post-it note and cover up. Okay, all that's over here is reactions, uniform load. Over here, reaction, uniform load, and that vertical load that we have. So here's my system. If I look at this side, I have 1, 2, 3, 4, 5. I have 5 unknowns. If I try to sum the moment here, I have an unknown AY, an unknown MA, and that is too many unknowns. If I sum it at the wall, again, I have this internal shear, but I also have this moment at A. So I can't use this. But if I look at my right-hand piece, I can sum the moments about this pin, and look at that. I can solve for dy. Or I could sum the moments about dy, solve for that internal pin, sum forces in the y direction to come back and get dy. So I'm going to call this one free body diagram 2. And we are going to start with free body diagram 2 for the solution. If you guys would practice like putting more detail into your solutions, number one, it's easier for you to follow back your process. Number two, when you come in for help, we know what you're doing. Number three, on exams, it's easier to give partial credit if, again, we know what you're doing. So free body diagram number 2, my rule I'm going to use is summing the moments about B. I'm going to use right hand rule positive, and here in statics and strengths, that MA is 0 because hopefully nothing's moving, okay? So let's just go from left to right. If I sum moments about this pin, those go away. So I'm going to have right hand rule negative 30 kilonewtons times 1.5 meters, okay, minus area, base times height, so I have 8 meters, times 10 kilonewtons per meter. Okay, if I look at my units, I'm only at a kilonewton, which is a force, so I still need to make sure I get that distance in there. This uniform load is 4 plus 4, 8 meters long, so the centroid is here at 4 meters. So there's my distance, which gives me a moment. I would say start writing units when you're solving your problems because it will always let you know if I'm working with moments, it's going to be kilonewton meters. I need to make sure that I have kilonewton meters on every part. Okay. And then plus, I have dy times 4 meters. That's all the forces that I have, and all of that equals 0. Okay. All the forces on the left equals 0 on the right. So I can move these over to the 0 side to isolate dy. So I have 4 dy equals, okay, 30 times 1.5 is 45 kilonewton meters. And it becomes positive. 8 times 10 is 80. Times 4 is 8 times 4 is 320. So I have plus 320 kilonewton meters. Okay. And now I can multiply by that reciprocal on both sides, and I get that dy equals, so we have 45 plus 320 is 365 times that reciprocal, so dy equals, I'm assuming I'm adding right in my head, so 30, 1.5, 8, 10 times 4 times, plus 4 divided by, I get 91.25 kilonewtons. Because this is a reaction, I know that I provide the magnitude, the unit, and I got a positive value. So I know that my assumption of it going up is correct. So at this point, I like to just go ahead and go back and write down what that reaction is. So I could go back to my overall free body diagram, and once I know this roller, I can use summing forces X to get AX, Y to get AY, summing moments to get MA. Or I can work my way through these smaller free body diagrams. And that's what I'm going to do is show you how to transfer through so you can work with smaller pieces. It's just, I think, a little bit easier sometimes depending on the loading. So if this is 91.25, do you think we can go back and calculate the shear at that pin? Okay, so let's sum forces in the y direction. And I'm going to call up positive. So I have that shear at B. I assumed it's up on this side, down over here, but on this free body diagram, it is up, so positive, minus 30 kilonewtons, minus uniform load, area, base times height, 8 meters, times 10 kilonewtons per meter. Unit check, kilonewtons, that's what I need to have, plus 91.25 kilonewtons, and all of this equals 0. So as I isolate that shear at B, I'm going to have 30 kilonewtons plus 80 kilonewtons minus 91.25 kilonewtons. So my shear at B equals, so let's just go ahead and add this up, 8, 9, 10, 11, whoops. I get a shear, a positive value of 18.7 kilonewtons. Now, I'm not going to call this up or down or positive or negative right now because I did assume it up. I got a positive value, so that tells me it is indeed going up. But if I call this up, okay, see how I called this up? What does up mean? On the right-hand side, it's up here, but guess what? On the left-hand side, it's actually going down. So I don't want to call this up because then I might think that I'm up everywhere. Okay, I'm just going to note that I got a positive value, and that positive value means my assumption of up is correct. So if we are 18.75 on this right half, I have to also be 18.75 on the left half. When I put up and down back together, I get 0. So when I look at my overall free body diagram, again, I don't see these internal forces on that overall picture, okay? If I had gotten negative, if I had gotten a negative here, then I would have said, wow, that means my assumption of direction was wrong. And I would have actually come back up to my free body diagram and I would have said, you know what, that actually really goes down. And I would be like, okay, if that goes down, this has to really go back up. So I'm really visual. I like to see what's actually happening. Some of you might want to just keep it directionally the way you started, but then call it a negative 18.75. That's not wrong, but you have to do one or the other. Either go back and change the direction, and the magnitude then is that positive value. If you don't change the direction, you need to call that value a negative, and that will correct your direction arrows. Okay, so now that I have 18.75, this looks very much like the diving board problem that we've done. It looks very much like a simply supported beam. So I can actually go back and I can sum forces X, I can sum forces Y, and I can sum moments to calculate these three unknown reactions. And I'm going to say this over and over. You should never have a wrong answer. Once I solve for dy and I solve for my forces and reaction at A, I should be able to go back to my entire free body diagram, and with those known values, some forces X, some forces Y, some moments about any point, because I've known them all now, and I should get indeed that the sum of my forces on the left side truly equals 0. Okay, so again, on your homework, check your work. Check your work, because if you're not getting that the sum of the forces equals 0 after we come up with these values, you've messed up somewhere. Either it's in a free body diagram or it's in your algebra. But it's the easiest way to figure out whether you are correct or not correct. Okay, so if you don't know how to do this, you need to go back and review simply supported fixed cantilever systems. Thank you.